To understand generative AI's limits, look at how it stores information. Once a model finishes its training cycle, its understanding of the world stops cold. Engineers refer to this as parametric memory. Every fact, concept, and relationship the model knows is baked directly into its pre-trained mathematical weights. It has no external hard drive to reference. Because of this architecture, every standard model operates with a strict knowledge cutoff date. If a news event occurs or a company updates its policies after that date, the system is completely blind to it. When confronted with a question it lacks the facts to answer, the system's statistical engine does exactly what it was designed to do. It predicts the next most likely sequence of words. It guesses. The result is a confidently stated falsehood, known as a hallucination. Historically, the only way to update a model's knowledge was to fine-tune it on new data. But running massive data sets back through a neural network is expensive and creates a significant data privacy risk when handling sensitive enterprise documents. To deploy AI reliably, engineers must decouple the model's language reasoning from its internal memory storage. The structural solution to this problem is a technique called Retrieval-Augmented Generation, or RAG. Instead of rewriting the model's internal weights with fine-tuning, RAG injects the necessary, up-to-date facts directly into the user's prompt in real time. Looking at this high-level system architecture blueprint, you can see how the components interact. On the left, we keep the language model static. On the right sits your secure, live enterprise data. Connecting them is a dynamic retrieval pipeline. By bridging these systems only during a query, sensitive organizational documents are never absorbed into the neural network itself. Data privacy is preserved. RAG provides the live context that allows a static language model to function as an active, context-aware reasoning engine. Building a RAG architecture requires constructing two sequential pipelines, the ingestion pipeline and the retrieval pipeline. We start with the ingestion pipeline. This is the preparation phase, where raw data is formatted for the system. The technical hurdle here is that language models cannot natively process raw text, they only calculate numbers. To bridge this gap, the pipeline first ingests raw company documents, like PDFs, and fractures them into small, manageable pieces. Engineers call this chunking, ensuring the original meaning remains intact. Once isolated, these text blocks pass through an embedding model, mathematically translating the raw language into dense arrays of decimal numbers. These vector embeddings represent the text's underlying meaning. Finally, they are plotted and stored inside a massive three-dimensional grid called a vector database. Through the ingestion pipeline, unstructured human knowledge is mapped out as precise mathematical coordinates that a machine can navigate. Storing these coordinates requires a specialized database because traditional keyword searches lack the necessary flexibility. In a standard SQL database, a search for heart attack symptoms rejects a document titled cardiac arrest because the exact characters don't match. But in a three-dimensional vector space, the query is converted into a vector and dropped into the grid. It immediately links to the cardiac arrest data points based on physical proximity. This is the mechanics of semantic search. Concepts with similar meanings are plotted physically close to each other, allowing the system to retrieve information based on intent rather than exact spelling. By utilizing physical proximity in a vector database, the RAG architecture achieves genuine conceptual understanding rather than blind character matching. With the database populated, the system is ready for the user-facing half of the architecture, the retrieval pipeline. When a user submits a question, that text is instantly converted into its own vector embedding, using the exact same model from the ingestion phase. During the similarity search, the glowing query vector enters the database, maps distances to surrounding points, and extracts specific data blocks. These blocks form the context. In the augmentation step, the system stacks the user's original query with the extracted context docs, packaging them inside a single prompt box. This heavily detailed augmented prompt is then fed directly into the static language model. At this point, the LLM is strictly instructed to generate its final answer using only the provided context blocks, ignoring its pre-trained memory. By forcing the AI to process an augmented prompt, its reasoning is constrained to hard, verifiable facts, neutralizing the threat of hallucination. The pipeline we just constructed is known as naive RAG, the standard baseline architecture. While naive RAG excels at mapping general concepts, it can struggle in strict enterprise environments. If an employee needs to search for a highly specific product SKU or a unique ID number, semantic proximity isn't precise enough. To fix this, engineers deploy an advanced iteration called hybrid RAG. This split pipeline shows how hybrid RAG solves the exact match problem. The architecture runs two searches simultaneously. The blue beam executes semantic vector search, while the green beam runs traditional keyword search. The system then merges the results into a single optimal output stream. Hybrid RAG ensures engineers do not sacrifice exact precision to gain semantic flexibility. Another limitation is that standard databases treat every chunk of text as an isolated island. This makes tracking complex legal or financial relationships between different entities nearly impossible. For highly relational data, the structural solution is Graph RAG. Watch the dots in this database map. Graph RAG organizes the data into nodes and connecting edges, mapping out exactly how different concepts, terms, and people interact within a complex web. But what happens if a user asks a multi-step comparative question? If you need to compare current asset prices against historical trends, a single database query cannot resolve it. This requires agentic RAG. Here, the system is granted the autonomy to break a complex query down into smaller tasks, pulling from internal databases while simultaneously querying external finance APIs or running live web searches. These architectures enable RAG to function as an active, autonomous problem-solving engine. The final layer of quality control is self-reflective RAG, or self-RAG. Before presenting an answer to the user, this architecture forces the model to critically analyze and score its own draft response against the retrieved context. When engineers stack these advanced architectures together, combining hybrid search, graph relationships, agentic autonomy, and self-reflection, they create a production-grade system. This complete modular structure provides a highly stable and deeply secure framework required for managing massive, high-volume enterprise-level data. RAG serves as the core architectural framework for deploying generative AI safely and accurately in the real world.